I'm now going to finish up chapter 14. We're going to talk about Diels Alder reactions. And these are reactions that involve conjugated dienes. And example of a pericyclic reaction mechanism. The pericyclic mechanism was discovered a lot later than polar and radical reaction mechanisms. All of those kinds of mechanisms were first presented back in chapter 6, and they just barely included pericyclic in that chapter. And I mentioned it at the time because I said, well, if we're going to talk about the kinds of mechanisms, we need to know all of them. And so this is the first time we really see what we mean by a pericyclic reaction mechanism. And the word means that the electrons move more or less in a cyclic fashion, and also they move all at once, and so we say that the reaction is concerted. And we're only going to see the movement of the pi electrons and changes in the orbitals in two compounds to create a six-membered ring. So they will always create a six-membered ring. And so we want to know what kinds of structures will work, and so they're kind of two parts. And one of the things that you need is a diene. And I've put the word quotation marks because you don't necessarily need two double bonds that are part of a carbon-carbon system. You can use other elements. So I have an example here that the diene is actually got a carbonyl in it. So it's just two, the conjugated system, a double, single, double, or a pi, single, pi system. And it has to be able to achieve what they call the S-cis geometry. In other words, it has to be able to curve around like this. So you could draw it. You could draw it curved like this. This double bond, this single bond right here can rotate because there's nothing preventing it from rotating. This one cannot rotate because it's pinned into this ring, but that's okay. Sorry. This one is in the right geometry. So you could think of it as sort of cis. And the reason that it's not truly cis because the term cis in terms of geometry refers to a ring or a double bond, and we're talking about this quote-unquote single bond here. So it's sort of like cis. But it's not truly cis in the strictest sense of the word. So here's another. So these are examples of things that cannot work as the quote-unquote diene because this single bond is not able to rotate. This one is forced to stay in a S-trans, or sort of like trans geometry. This one can't work because this pi system is part of a triple bond, and this carbon is sp, and so this is a linear portion of the molecule right here, so this pi system can't get close enough to that pi system. So you can't have triple bonds as part of the diene. This one can't work because it's too crowded, and I didn't do a space filling thing here, but these two guys, if this is a cis structure on this double bond right here, it really wants to flop around and get this guy on the other side. So it's going to spend most of its time like this, and so it really can't undergo this reaction either. So you really have to think about that as one of the requirements for this reaction to work, is a diene that can get into the right geometry. The other thing that you need is called a dienophile, and that means something that loves the diene. And there's generally going to be some electronegative element in there that's close to a pi bond. So the other guy needs a double bond, just a double bond, and although it could have more. And so in this case you've got a chlorine atom, and so I've drawn that out a little bit. So here's the pi system and this electronegative chlorine atom, and so the orbitals are kind of pulling electron density away here, and so that's vinyl chloride is the common name for that. That will work, or if you got another electronegative element in conjugation with your pi system, that will work. And here's another example. And acetylene also works, but these are the most common things. Is you have conjugated systems, but the carbon-carbon double bond acts as the dienophile, and because it's the electron deficient due to the nearby presence of that other more electronegative element. And this is kind of a template, okay? You really just need to learn sort of the sketchy template way of looking at this. So you've got the conjugated diene that's in the S-cis configuration, and the whoever's going to be the dienophile is going to be some other pi system. And you're going to connect the ends of those and make a six-membered ring. Remember I said in the first slide, you'd always make a six-membered ring. And this template is really just a template because this molecule right here is just ethylene, and it's not a good dienophile. Why not? Remember I said you needed an electronegative element nearby to help make it more electron poor and make it attractive to this diene, and ethylene doesn't have another electronegative element to help make it be a good dienophile. So if you put these two guys together, it would take months to get any amount of product at all. But it's very simple, you know, a conjugated diene, so you got 4 atoms and 2 atoms, you get a six-membered ring, and whatever decorations you have on here and whatever decorations you have on here, you just add them on. And remember, the product is all going to be a six-membered ring. You have this pi system, it's conjugated, so it's one long extended pi system, this little short pi system. The electrons move around cyclically to make this and this new bonds, and the 3 existing pi systems end up just with 1. So here's kind of an orbital picture. Again, one of the things that you kind of have to realize is kind of like, if you ever seen those guys in the circus or at fairs, carnivals that make animals out of little skinny balloons, and you know, if you squeeze one side, the other side gets bigger. Well, this is like this bottoms of these orbitals approach the top of these orbitals, so they don't actually come at each other side by side, kind of the way it's drawn here. It's really coming from the top or from the bottom. But we're going to connect this end and this end together, and so they've drawn it kind of to get the hydrogens kind of out of the way. And so here's where the pericyclic rearrangement happens. Remember, you're going to get a six-member ring. So this is the template. It's the same thing I just drew in my template, but they just added all the hydrogens in there. Okay? And so you get a six-membered ring. So we're going to connect the ends of the diene to the ends of the dienophile. And so we're going to make bonds here. And remember I said they kind of approach from the top or the bottom. So you're connecting the ends of sorry, this is another molecule. The ends here, and so you're making a six-membered ring, and then you just add on the decorations. So there's nothing else out here, so they're just not drawn in, but you had this thing hanging off of here, okay? And you just put them together and heat it up a little bit, and they just work. So here is this is a cyclopentadiene ring. Again, the ends of the diene with the ends of the dienophile, and you get a new six-membered ring. Well, here's the new six-membered ring. Here's the original five-membered ring, but you're always going to make a six-membered ring. So this is the new six-membered ring, and they drew it like this because that's really kind of the shape it takes. And the other thing they wanted you to know about this particular example is it tends to favor what they call the endo product, so it's kind of cup-shaped instead of coming in from the other side because this guy's in the way. When you draw this on a piece of paper, you don't necessarily see this three-dimensional shape. It's a little easier to see with molecular models. And one other thing you should know, the geometry is conserved. We said that it was a concerted reaction, so all the electrons move at once. So if you start out with a cis alkene, you're going to end up with those groups that were on that alkene still on the same side. So here's a cis alkene. So this group and this group are cis to each other. They're still cis to each other in the final product. We're just connecting the ends here and the ends of this diene with the ends of this alkene. Here's our new 6-member ring, and these guys stay on the same side. Or if they were trans to each other, again, if you think about it flat on a piece of paper, it's a little harder to see, but remember, he's going to approach from the top or the bottom, so it's okay, it's not in the way. We just connect the ends, and these guys are trans to each other, they stay trans to each other. So it will help a lot if you look at examples to recognize that. And just also, I mentioned earlier in this section that we aren't limited to carbons, and in fact some molecules can dimerize and in kind of interesting ways. So here's this molecule can act as either the conjugated diene or as the dienophile, because it's got that electronegative oxygen to pull electron density away. So if you put this stuff in the right conditions, it will just make these molecules that are 6-membered rings. It happens that the oxygen is one of the members of the ring, because there's, you connect your ends, okay, and then you've got this. But if they went together this way or if they go together this way, you get two different molecules. So if they go together this way, it's the same molecule drawn exactly the same way, then I flip this one, okay? So in this case, the side chain aldehyde is further away from the oxygen that's part of the ring than it is here. So it's either next to it or 3 atoms away. And you get about a 50-50 mix. And so that's the kind of the complicating factor when you have these heteroatoms. Sometimes, you know, you get mixtures. But I did want to show that you're not limited to just carbons in making these rings. And by the way, a lot of these Diels Alder reactions are reversible. So let's look at a structure and say, I wonder if you could make this using a Diels Alder reaction. And so what are you looking for? Remember that the Diels Alder product is always a 6-membered ring, and there's going to be a double bond in there. And so where were the new bonds formed? Okay, so remember the diene is this part of it, and then the alkene, the dienophile, is the other part. So the new bonds have to be these two guys right here, okay? And so this was the diene, and this is the dienophile. And so we just draw that in, okay? So because this molecule is symmetrical, it doesn't matter how we draw this. If we flip it over or whatever, we're going to only get one product. So you can look at this kind of a structure and you can figure out what would have been the starting materials to make that using a Diels Alder. So in this part of the chapter, you need to be able to recognize structures that would be suitable as dienes or as dienophiles, and what the rules are about that. You know, being able to achieve the right S-cis geometry, having electronegative elements for the dienophiles. You should be able to draw or recognize products of Diels Alder reactions from given starting materials, or if you have a product, to be able to tell what would have been the starting materials that would enable you to create that. And that is the end of chapter 14.